Okay, so if you take a natural number, and I'm talking about natural numbers here as in 0, 1, 2, 3, 4, 5, 6, 7, 8, so including 0, if you plug it in for these n's here, then this entire quantity here is going to be a natural number. So if you don't believe me, you could probably do a proof by induction. Probably wouldn't be too hard, but there is a cooler way to do it. You can think of this number here, the 1 plus root 2, as being lambda 1. 1 minus root 2 is lambda 2. And these are the roots of a characteristic equation of a recurrence relation. A linear, etc., linear, whatever they're called, recurrence relation. So these are the two values, and now we have to find the characteristic equation. So if you real quick think about this geometrically, 1 plus root 2, that's going to be like here, 1 minus root 2 here. So the characteristic equation is a quadratic, so you can think of it as a parabola. And so you could draw a parabola going through here, you could draw another one going like this. Point is, there are infinitely many different parabolas that go through these 2 points. So the A, B, and C of the characteristic equation aren't determined. So if you could think 2, okay, well this is under the radical, so this 2, that must be b squared minus 4ac. This 1, that must be the negative b over 2a. And you can try to figure it out like that, but that's just like pretty hard. So it's easier to just look at, you could just say lambda minus the first root, and lambda minus the second root. This thing is equal to 0. And then, so this would give you that lambda is equal to 1 plus or minus root 2. And if you don't like the equation that this ends up giving you, you could always multiply by a scalar here, and that's just going to change your vertical stretch of this parabola. It'll give you all of the different possible parabolas going through here. So, so if you want, you could regroup these, say like lambda minus 1 on both of these, lambda minus 1, and then have your minus root 2 and your positive root 2, and you could do a difference of squares. Or you could just believe me, because I reverse engineered this problem, and so I already know what this is going to be. Let's see, I don't have it written down here. It's minus 1. This is what you get. Okay, so now what? Well, this means that the corresponding recurrence relation for this thing is going to be fn plus 2 minus 2fn plus 1 minus fn is equal to 0. And you can rearrange it, and you see fn plus 2 is equal to 2fn plus 1 plus f of n. So that means if f of n and f of n plus 1, if those are both positive integers, then fn plus 2 must also be a positive integer, because you add a positive integer to another positive integer and you get a positive integer. So then all you have to do is find out what initial values this thing would have. So this equation here, we know that this has the solution. Fn is equal to c1 times the first root, which is 1 plus root 2 to the n, and then the other one. And so clearly this is the same thing, this is the same form as this. The first coefficient, the c1, is just root 2 over 4, c2 is negative root 2 over 4. So then all you have to do is find out what are the initial values. You plug in 0 here, you have 1 minus 1, that's 0, that cancels out. So you see that, so f0 is 0. What about f1? Well, plug in 1 here, get 1 plus root 2 minus 1, so the 1's cancel out. It looks like you're going to end up with 2 root 2. So you have 2 root 2 multiplied by root 2. 2 root 2 times root 2, that's 4. Divided by 4, that's 1. So So f1 is 1. And so, since this is the recurrence relation here, f0 is an integer, non-negative integer, f1's also non-negative integer, so that means that all of these next ones must also be non-negative integers.